Hello everyone, and welcome to our latest installment of Build Your Simulation CFD IQ. Today's presentation is about best practices for 2D modeling in Autodesk CFD. My name is Marwan Azzam. I'm a technical support specialist with Autodesk, and with me is Matt Bemis, also a tech support specialist.
Hi everyone, my name is Matt, and as Marwan said, I support CFD here.
So today we're going to be talking about building models for 2D analysis. So let's go ahead and get started. So contents of today's discussion, we're going to be talking what is 2D, how to extract a 2D model from a 3D CAD model, some CAD considerations, planes of symmetry. I'll be talking about boundary conditions, a little bit about post-processing and the results, and Matt is going to do an example of a diesel fuel injector, and he's going to go through all the setup that you would do in a 2D model. So first of all, what is 2D? Well, in real life, there's nothing that is 2D. Everything is 3D. So a 2D model in FEA, not just CFD, FEA in general, a 2D model represents a cross-section of the full 3D geometry. So you're taking a plane of cutting your model along a plane. In this case, it's going to be the XY plane at Z equal to 0. That's how it's set up in CFD. It has to be the XY plane. And that will be the cross-section of that 3D geometry will be your 2D model. And 2D models can be one of the three following types. Either a Cartesian 2D, where the geometry, the 3D geometry that you are representing does not change in the Z direction. And when I say geometry, also the boundary conditions, the inlet, the outlet, all of those don't change in the Z direction, not just the geometry. Or it could be an axisymmetric in X, where the geometry is rotated about the X-axis, or axisymmetric in Y, where the geometry is rotated about the Y-axis. The next slide here is going to show an example of what I'm talking about here. So on the left here, with a 2D axisymmetric, your model is that plane, the outline in blue. That would be your 2D model representing the full 3D model, which is rotated, of course, 360 degrees. So this is a 2D axisymmetric, and your 2D model actually represents a 1 radian slice, not just a plane. I mean, the model is just a planar model, but it represents a 1 radian slice. In a 2D Cartesian, your geometry doesn't change in the Z direction, and your model is again that same slice. So that model, the 2D model, can either be a 2D Cartesian or a 2D axisymmetric, depending on your actual 3D geometry. And in a 2D Cartesian, that slice represents 1 unit of length in the Z direction. So your model, that cross-section, is in the XY plane, and the dimension in the Z direction would be 1 unit, whatever your units are, be it millimeter, meter, inch, whatever it is, it's 1 unit. And that's very important to know when you set up your inlet boundary conditions or outlet, whatever. If you have a flow rate, that area is either based on a 1 unit in the Z direction, or in the case of a 2D axisymmetric, it's based on a 1 radian slice. So you need to be aware of that, such that you set up your boundary conditions properly.
Marwan,
So,
I'm just gonna touch on that again, just because people do get tripped up and ask questions here. A lot of times when you set units in CFD, I don't really care if it's millimeters or centimeters. I'm kind of going on the fly, and it's all in my head. But this is a place where it really, really matters, because I've seen people use, several millimeters per second of the volume flow rate generation and have their base units in meter, and they don't have any flow, and they think something's wrong going on, something bad's going on. So, when you have units that are 3D, you really just have to be, smart about how you're analyzing it. And, great thing about 2D is pressures and velocities are kind of the same, because those aren't 3D systems. But yeah, super, super important for 2D.
That's right. Thank you, Matt. Now, maybe before we go on, let's see where that slide is. That why would you want to do a 2D analysis? Maybe Matt can tell us why.
Absolutely. So the biggest, answer is solve time. Really, basically, if you're gonna, run some simulations during your design process, chances are you're going to run a bunch and iterate. And a lot of times you can get a lot of answers very, very fast, really early on in the design cycle, and you can keep iterating your design. So the amount of time that's saved is kind of mind blowing. It's probably hard to quantify, but at least 10 times, if not more. And it allows you to just get more design cycles, which is cool. It also, if you're trying to simulate something that's really challenging and you're sort of intimidated by it or having no luck getting good results, starting with 2D will save you a lot of time. I do it sometimes. Sometimes I take customers' models and bring them from 3D to 2D and troubleshoot, because if it's going to take me, 10 or 15 different tries or tweaks to get it right, I can't wait one day for every technique I change or try. I gotta try, like 1 per hour or something like that, or faster. So if you're getting divergence or bad results, or you want to kind of do like a turbulence model study and you have some experimental data or something, or what a plume's going to look like or something like that, and you want to crunch the numbers fast and go with the turbulence model that matches what you're looking for the best, then 2D is awesome. So later on I'll go into my example, and I was running simulations in 10 minutes instead of 10 or more hours, so it was really cool.
Yeah, so I mean, go ahead.
Go ahead. I'm good.
No, I mean the geometry, that's a subset of what's out there that people are modeling, things that can actually be 2D, because it's either evolved 360 degrees or it doesn't change in the Z direction, as well as the inlets and outlets. They are symmetric like that, either 3D axisymmetric, or they don't change in the Z direction. But maybe the flow inside is not completely 2D, but still, even though you're making that assumption, like Matt said, that you can make so many iterations and tweak your design before you go into 3D. So 2D, in other words, 2D might be it. That's all you need to do. Or 2D might be the beginning, where you run so many analyses using 2D, and then you do the full thing in 3D. In either case, you are saving a lot of time. Before we go into this example here, let me show you a couple of things. So how do we get a 2D analysis into CFD? So here, what I'm looking at is a model in Inventor. So that's the model that we saw on the slide here. This would be a 2D axisymmetric model. So if I pull this feature here, this is what it looks on the inside. This is a quarter section. So one might say, okay, I'm going to draw a sketch where it's going to be basically just the outline. And that really isn't enough. If you try to just import this outline here, CFD will not like that. Let me start CFD. Can you see my screen?
Marwan, the UI might have locked up again.
Oh, that's all right.
All right, now we can see.
Okay. Yeah. So I'm going to go to File, New, and browse here. And if we pick up just the wireframe IGES file and try to open that, give it whatever name, it will not like that, because that wireframe is just the wireframe. It is not surfaces. So what I'm trying to say here is that your 2D model, your CAD model, has to be is surfaces, not just the wireframe sketch. So what you would need to do is you would need to go in and make surfaces. So I'm going to open this wireframe, this IGES wireframe here. Oops. And just show really quick how to work with it. So if this is just a sketch, in this case it's not even a sketch here, but even if that was a sketch, it will not import like we saw. So what you need to do is you need to, for instance, in Venner, we call that patching. When you do it to patch here, it would actually make this a surface. And if you had multiple parts, each one of them would be its own surface. So I would click on patch. Now again, if this was a nice sketch, all I need to do is select one edge, it will select the whole thing, and it will create the surface. This involves me clicking a few more, actually all the lines, but you'll see the end result is going to be the same, which is a surface patch based on this outline. So I will hit OK, and now it's a surface. And if I go ahead and save that, I'm just going to call it surface. If I save that IPT part and go into CFD, actually I should be able to launch it from here. I know I don't have it, no problem. Let's just so where is my model here? Here it is, Surface 2D. That will import properly. Okay, here we go. And here is our model, obviously in the XY plane at Z equals to 0. So just the wireframe, be it a wireframe or a sketch, wouldn't work. It has to be surface, a surface model. And I can make a decision here whether I want it to be 2D Cartesian when I right click on geometry, or I can change it to axisymmetric in X or axisymmetric in Y. And obviously this is axisymmetric in X, and since this is touching the x-axis at y equal to 0, this, the inside radius is 0. Of course, you can have something like a cylindrical shape. If this line here was not at y equal to 0 but positive, then you will have basically an opening in the middle. So again, it's revolved 360 degrees around the x-axis. At this point, I'm going to go ahead and make Matt the presenter so he can show you the model that he did.
Thank you, Marwan. Just give me a second. Marwan, can you see my screen?
You have the presentation up. Yes, we can see the presentation.
Yeah, I gotta. So I decided to model in 2D a fuel injector, a diesel fuel injector. These basically just sit right in the head of a diesel fuel engine and use a needle valve to spray diesel fuel straight down into the cylinder. There's a couple of reasons why I wanted to go 2D here. I've noticed a lot of folks lately having hard times getting enough elements through cross sections or ports in flow areas. So a while ago, I've helped some people try to model nozzles and other things like that. You know, in order to capture flow, you got to have a very minimum 3 elements through the thickness of your flow section, and that can just drive your element count to be unrealistic. So I thought this would be a great application to kind of show. So I just thought that was a really cool picture. This is just a cross section of a engine. You see the 3 cylinders there. In the very center of the cylinders, right above the fuel injectors sit up there. They're in between the springs on the valves there. So they, you know, sit there. Now these fuel injectors usually are supplied, you know, diesel fuel at over 15,000 psi. The newer ones are much higher than that, but even like in the 1920s or 30s, they were up at 15,000 psi. And just depending on the engine, basically compression ratio would be a few hundred psi. So they got to get that fuel, you know, injected as fast as possible. Yeah, so on.
Sort of direct injection here.
Yep, exactly. And my schematic wasn't great. There's basically just a needle at the bottom that plugs a hole, and there's diesel fuel around it on the inside of the very end of the injector. And a solenoid or newer technology uses a piezoelectric device, pulls up the needle, which is forced into the closed position on a spring. So you hit the solenoid with electricity, it pulls it up. Let's go. Same thing. Yep, that's pretty much that.
I mean, this model, Matt, you modeled this as a planar Cartesian 2D, correct?
Yeah, I modeled it as a planar 2D Cartesian. It wasn't a perfect application for axisymmetric, and I'll show you why. Basically, let's go back a few slides here. Okay, so I wonder, Marwan, you can see my mouse, right?
Yeah, I can see the mouse.
So the fuel comes in on the side here. It comes down this, this port, and this here is the needle, and the needle goes down to the center. So if we were to have it be axisymmetric around basically the origin, looking at like a top view of this, we would be swinging the fuel, the fuel port or the pathway around in 360 degrees. And that's not really what I'm trying to do here.
It'll be a cone, basically.
Yeah. And that's not what I'm trying to do here. I really just want to look at a cross section and say, if this is a pressure-driven flow, what are my velocities going to look like? Maybe look at some pressure, internal pressures on the devices. With such high pressure, you're going to need really strong components on the center pieces. So understand those wall forces, things like that.
And the reason I bring that up is because unlike a 3D model where everything is in front of you, a 2D model, you have to use your imagination a little bit. So you have to imagine what it is really doing or representing in the 3D world.
Sure. Yep. And you just definitely have to, take it into account, think a little critically. That's all. So I grabbed this off of GrabCAD. This is, I think it was a Bosch fuel injector. And it was cool because all the inside components were there. The spring that forces the needle down, There's even a breather for the spring chamber, things like that. So this kind of represented pretty close to a, manufacturing ready piece of CAD. One thing I do want to say here is that if you're going to run with 2D, we're going to end up putting in a midplane and kind of going from there, but it's much easier to defeature first. So then when you're looking at this midplane, there isn't a million different, pieces, solids and lines and things like that. So of course I filled in, those screw holes, that cap on the top, some, general fillets and stuff, really just cut it all off. The majority of this model, like for what you can see, is going to be suppressed anyway. We're going to fill the internal volume and just have a flow path. So, yeah. Anyway, I filled in a ton of it just with solids, just extruding through different pieces of it. That was just a cool cross-section view of the original piece of CAD. You can see here's the fluid path. In this model, it actually wraps around and goes through the other side of the injector, and I actually rerouted that because I wanted to go straight down. Obviously, if you're going to do 2D, you can't have something go into the depth or into the thickness. So basically, I ended up doing a midsection plane here, and then used project and grabbed either the edges or tried to grab bodies. So I did that in SimStudio Tools because I spent a ton of time, making stuff simulation ready there. But I know you can project in Inventor, and I've done it before. It's pretty common. So that's what my 2D plane looked like after, which was pretty cool. I only see maybe 5 or 6 pieces there. Basically, when I had the sketches, just like with Marwan, I patched them all, and then I even stitched a few to kind of get continuous pieces. So the needle valve is down there, which is blocking. I ran this a steady state, but and this is a good application because running this in 3D at steady state would be really complicated, but introducing motion and doing transient, which obviously these injectors are in real life, it'd probably be pretty much impossible. So it'd be really cool to take this a step forward and do a transient, kind of like a cycle of an injection, for whatever period of time these things stay open, and see what it looks like. I used a manual mesh because I basically wanted to have enough elements through the thickness of that fuel pipeline. I'm sure everyone knows manual meshing is uniform by default, and it's based off the edge length, so I could specify an edge length. And here with 2D, you can pretty much be greedy with how much mesh you can throw on it. You're not going to have solve time problems. So in terms of the fuel volumes, there's 2. There's basically the main one, which is the inlet, the fuel pipeline, all the way down to where the needle valve and outlet sit. And then there's a small one right around the needle valve, which is suppressed in the outlet area. So I had 0.03 centimeter element size on that bigger part up top, and then 0.007 centimeter element size down below. So it was pretty incredible. This only produced 39,000 elements. Solve time was like 10 minutes pretty much. And I was running about 1,500 iterations. So it wasn't just a quick solve time. Or it wasn't a default convergence. I ran it to tight convergence and got a lot of iterations out of it. Now you can imagine using those element sizes, you would absolutely never be able to run this in 3D. It would, or at least with those, if you wanted to run it in 3D, you would have to sacrifice on mesh, which is definitely not ideal. So moving on. So here's two pictures of the mesh. On the left is that coarser mesh up top. The element size looks similar between these two pictures, but it's just because one is zoomed in a lot more than the other. On the left is that 0.03, I think, that bigger mesh. And you can see there, we talk about having at a very minimum 3 elements across the thickness. 4 is probably better. I have way more than that, probably 8 to maybe 10. I'm not sure, but there's definitely enough there. And on the right side, which I thought was kind of incredible, is that my channel across their diameter there basically is 0.354 millimeters, which is really small. And again, I have tons of elements, maybe 10 or something, through that thickness. So this is just really great stuff. A lot of times people struggle with getting quality meshes through tiny gaps in your model. And in glazing over or sacrificing on mesh is really not the right thing to do, because you might get results, but the results are not going to be good. So you can see here, my mesh is or my results are mesh independent. You can't see elements, things like that. So now I can pull up CFD and kind of show the results a little bit. All right, so here's CFD. Marwan, you can see the program.
Yeah.
Right?
Yep.
Okay. So again, I had that I used 250 psi gauge on the outlet. It's a bit on the low side, maybe like old diesel engine or something like that. And then 15,000 on the inlet side up top, which I looked up. I mean, they can go much higher, up to 45,000 psi, but this was kind of a first pass sort of thing.
One thing, Matt, here, since you're on the topic of the boundary condition, you notice one thing when you have a 2D model. So of course, in the 3D world, that inlet and outlet, these are actual surfaces. But in a 2D model, they are no longer surfaces. They're actually lines or edges. So Matt selected an edge to apply that inlet boundary condition and the outlet boundary condition. And you can see that up in the volume is grayed out, and you have surface and edge. And for what you would normally apply as a surface boundary condition in a 3D model would be a surface here.
Yep.
It would be an edge, I'm sorry. What would normally be a surface would be an edge. So that edge actually represents a surface, but you're selecting it as an edge.
Right. And that's why, if you have tons of data on what you're simulating, I would always go with either pressure or maybe velocity, because, volume flow rate is just going to make you think a little harder. But, in 2D, 3D, pressure's pressure. In the flow direction or across the flow direction, it's all the same. And velocities are really easy enough. You just have to make sure you're prescribing the correct velocity. So yeah, I just want to kind of show you my results now. Just because sometimes people ask, I mean, zooming in, you really can't see the elements here, which is a good sign. If you could see gradients, like you could almost tell where the elements are across results, basically by the color texture. It's a huge red flag. Here, I could probably bet that there's an element right there. It's not really in a super critical area, and it is there, but even that one's pretty hard to look at. And overall, I think the results are pretty nice. Go down to the bottom, this increase, in pressure at the restriction or at the, the smaller pipe area, shows nice gradients, as well as this outlet here. So if we just go to setup, basically this would be my needle that's lifted up up and down. And by the solenoid, of course, and there's my leakage path, I guess. Yeah, so again, I ran this 1,400 iterations. Maybe took 20 minutes. I don't think it did. And so it's really great. Now you know what kind of velocities you're going to be seeing in there. You can look at pressure forces on using the wall calculator on the needle and on the aluminum walls and other things like that. You can begin to understand the structural loading that your nozzle's gonna see and that your needle's gonna deal with the diesel fuel pressure. I can pull open some studio tools here. Again, here was my original model, and I basically let me show you a section analysis. I already have one made. Okay, so again, this is not simulation ready, but what I really did was put a plane at the midplane, and then split all the solids, all the parts, whether they're components or bodies, and then hid half of them. Hid one side, and so then I was kind of viewing this without actually using the section analysis, basically. And then you just start, you project, which is it's in modify. It's gonna make a liar of me. Oh, sketch. Yeah, so then you project onto a plane, and start grabbing edges. It's not too tough. You'll notice here I have I have 9 surfaces. I'm sorry, that's the wrong thing. I think I have, so I only have 5. So really simplified things, and was great. Marwan, is there anything else you want to see on my side, or?
No, I think that was good. There's nothing else that you missed. I mean, the basic idea is, first of all, conceptually, you have to, before you start doing your model, say, okay, would I benefit from doing this as a 2D? Can I do it as a 2D and then work from that point to create your 2D model by just taking a slice and prepping that model? I mean, the basic idea is, if you can do 2D, you should definitely do it, especially if you have multiple iterations that you want to do, because the time savings are going to be huge. And like I said before, it might not be your end goal, but it gets you to your end goal much, much faster.
Right. And it just, it lets you figure out the hard or work out the hard lessons, fast, basically. So you're not spending tons and tons of time. So with that,
do you have any questions?
Yeah, if there are any questions, please chat us in the window, and we can go from there.
Okay. Okay. We have a question here that says, that this geometry is neither 2D Cartesian nor 2D axisymmetric. That's correct, and we did kind of mention that at the beginning. Yeah, because it's basically a series of 2D axisymmetric sections of this model. The whole thing is neither actually 2D Cartesian because certain sections are involved, neither is it fully axisymmetric because otherwise you would get cones. So this is definitely an approximation. It will allow you to gain an understanding in how the flow goes in a relatively short period of time. And you can take that knowledge and apply it and make any design changes that you think are necessary and then incorporate those into the full 3D model. So yes, you have a point, and it's basically a spectrum too. So this might lie on one end of the spectrum where you're approximating you're taking a bigger than usual assumption about the geometry, and then on the other side of the spectrum, like the example I showed, which is fully revolved, you're not really taking any shortcuts with the assumptions. It really could be a fully 3D axisymmetric, or in certain cases a fully, not 3D, 2D axisymmetric, or a fully 2D Cartesian. So it's a spectrum, and the user has to decide how to proceed. Correct. Sure.
Yeah, I agree. And a lot of times I think these, we're going to run simulations on design. Your question might be, okay, we have 3 designs, which one's going to be the best, kind of thing. And if you can compare them, apples to apples, I still think you can pull a lot of great value out of that and knowledgeable. And then, and then it's time to go chase 3D or something like that. And, you're right, CFD can't really apply, axisymmetric to around, a certain part on some parts of the model and a Cartesian on another. It's just, a limitation. And, but so we kind of just went with, what was there and how can we extract some useful results.
Okay, another question is, how about, also pertaining to this injector model, Matt, how about solving the problem as axisymmetric in X, but reduce the width of the inlet channel to be equal in area with the original model? I guess we'll have to look at the model to really see what this is referring to.
My concern there is that you start sweeping the supply port. So it ends up being like a thin-walled layer.
Funnel.
Yeah.
Like a funnel, basically. Actually, a funnel would be, if you take the volume of funnel, yeah.
Or it ends up being like a fuel jacket, where it's kind of like a large pipe or something like that. But anyway, there's a couple of different things you could try there. Someone's asking about, is it possible to get 2D Cartesian model from a Revit model? That's a great question, and I'm sure you can, because we're just dealing with sketches here. I think the steps might be a tiny bit more involved, but I mean, considering CFD can already, open Revit models, I think you can pull some useful results from there. Marwan, what do you think? I bet you have a little more insight.
Yeah, I know Revit is a bit complicated. I've worked with it before a little bit. If you can do a slice in Revit and extract that cross-section out of Revit, then yes, definitely can do that. Otherwise, it might involve a couple of steps where you might export the Revit, maybe as a neutral file format, open that, and some studio tools, and proceed like Matt did with projecting the sketches onto a plane.
Yeah,
you might have to say yes or no. I would say yes, you can get it.
Yeah, you might be able to save, the wireframe and then patch it in some studio tools, which obviously, is free and comes with CFD, and it's a great prep tool. I don't think it would be too hard.
All right. I don't see any other questions on the question panel. I think that brings us to the end of this webinar. I would like to thank everyone for attending, and we hope to see you in one of our upcoming webinars.
Yep. Just one last note, of course, in the bottom there, if you want the slide deck, we'll be posting it shortly after the presentation. And this will be posted on YouTube later on our simulation channel, so you can reference it at any point. So with that, thank you for attending, and we'll see you next time.